This is example 4 on 2.6 rational functions day 2. So pause the video now and factor the numerator and the denominator completely. Okay, my numerator factored into x times the quantity x minus 2 times the quantity x plus 2, and my denominator factored into x times x plus 3. First thing I always look for is wholes. Do I have a factor that will divide out of the numerator and the denominator? I do. My x will divide out. People always seem to forget about this factor, okay? So if you see an x by itself, right, that can be divided out, remember that that corresponds to a 0 for your x value for your whole. And then we want to take a second and evaluate out of our reduced function. So for my reduced function, I would have x minus 2 times x plus 2 over x plus 3. So that's my f of x. That's my reduced function. So now if I find f of 0, that will be negative 2 times positive 2 over 3, which is negative 4/3. Sorry about that. So my whole is going to be 0 and negative 4/3. Okay, I have to be careful here though. Plugging in finding f of 0 is the same as how we find our y-intercept. So since we have a whole at our y-intercept value, that means we actually have none for our y-intercept. Okay, we want to be careful that we don't say that the y-intercept is 0, negative 4/3, because at that position, x of 0 makes our function undefined, which means we have a discontinuity, we have a hole there. So now, looking at our function, we want to see if we can start doing some of this more mentally instead of taking time to write out the work. So looking for a vertical asymptote, right? I want to look and see if there are any factors left in the denominator and find out what values would make that factor equal to 0. So the remaining factor is x plus 3, so our vertical asymptote is going to be x equals negative 3. Again, super important, it needs to be an equation of a line, so it needs to have that variable x in there. Looking at our horizontal asymptote, our degree of our numerator is 3, our degree of our denominator is 2. Since the degree in the numerator is larger than the degree in the denominator, that means we have no horizontal asymptote. So, thinking about our slant asymptote, the degree in the numerator is 1 greater than the degree in the denominator, right? This degree is 3, this degree is 2, 3 is 1 more than 2. So that means we do have a slant asymptote. So, in order to find our slant asymptote, we take the denominator on the outside and the numerator on the inside. So I have to be careful here. Remember that you need to put placeholders. So I'm going to put x cubed plus 0x squared minus 4x. So pause now and do your long division. Okay, you can actually pause once you get a linear factor here. You don't have to continue with your work, okay, because the remainder is not important. Our slant asymptote is always going to be y equals this linear factor part. So we're going to write our slant asymptote in as y equals x minus 3. So again, if you are not ready to do this as mental math, that's fine. But to find our x-intercepts, we're always setting the numerator of our function equal to 0, of our reduced function equal to 0. So for our x-intercept, I see my reduced function, I'm going to have 2, 0, and I'm going to have negative 2, 0. Okay, again, 0, negative 4/3 would have been an x-intercept. No, sorry, that would have been our y-intercept. Yes, so we find these two x-intercepts. Again, if you need to do that out for our x-intercepts, you're always setting the numerator of reduced function equals 0. Okay, so here I would have x minus 2 times x plus 2 equals 0. That gives me 2, 0, and negative 2, 0 as my points. Okay, the same way I found with mental math. Okay, so looking at this, I'm going to again make a table. I know that negative 3 is where my vertical asymptote is, so I'm going to try negative 4, negative 6, and negative 8 to see trends that way. And then I'm also going to try negative 2, 2, 4, and 6 to find trends that way. So pause the video now and calculate using a calculator or by hand those values. So right now I filled out this table. Okay, I just put sort of decimal approximations because those are easier for me to graph. These are sort of all approximate values. Okay, but they do help me to graph easier. Looking at this, I don't have a wonderful sense of sort of what the graph looks like, but I do see that at negative 4, I need to be at negative 12, and since that really is in the middle of my x values, and I go sort of up and down from there, I am going to change this so this is negative 20, and this is 20, but I think I can keep this as 10 and negative 10. So I want to graph my vertical asymptote. That's at negative 3. My x scale is 1, so I'm just counting over 3. I'm putting in a vertical line. I don't have a horizontal asymptote. For my slant asymptote, I have a oblique line. My slope is going to be 1 over 1. My y-intercept's going to be negative 3. So the way I think of this is I begin at negative 3. This was 2. This will be 3. And then I need to go up 1 and right 1. That's going to take me forever, so I'm actually going to go up 2 and right 2, up 2 and right 2, up 2 and right 2, up 2 and right 2. I'm just making sure that that's correct. I might need to think when x is 10, y should be 7. Sorry, I did my scale wrong because my x and my y's are different. And when it is 5, then it would be 2. And when it's 3, it would be 0. And when it's negative 3, it would be negative 6. And when it was negative 10, it would be negative 13. 2, 4, 6, 8, 10, 12, 13. And it was negative 5, it would be negative 8. Okay, So now at -8, I'm at -12, 2, 4, 6. At -6, I'm at -10.67. At -4, I'm at -12. Okay, so I know slant asymptote means as I go to infinity, I sort of approach that slant asymptote, and I can see that this is moving. So on the vertical asymptote, it would be going down. Okay, and then on the other side, at -2, I'm at 0. At 2, I'm at 0. I should have a hole at 0, -4/3. That's a little bit more than 1. And looking at this, I think I want to go back and find values to be more exact, for, oh, -2 should be 0. Okay, so I guess I don't need those. I can sort of see here. I know that I have to be going to positive infinity, so it'll have, or negative infinity. So from the trend of the graph, I can see that I go up. And at 6, 2, 4, 6, I'm at 3.55. And at 8, I'm at 5.55. And at 10, I am 7.38. So I can sort of see how I'm trending there as well. Okay, the best thing for these is seeing a lot of these, seeing what the branches look like. Okay, these separate pieces are called branches if you're discussing them in Communicate. Our domain for this, we go from negative infinity. Our first problem is at our vertical asymptote, which is at -3. Then we go from -3 to our next problem, which is at 0, our next division by 0, and then we are okay all the way from 0 to infinity. Around our vertical asymptote, as x approaches -3 from the left, we can see y approaches negative infinity. As x approaches -3 from the right, we can see y approaches positive infinity. Okay, here's -3 to the left, we're down at negative infinity. Here's -3 to the right, we're up at positive infinity. For our end behavior, as x approaches negative infinity, y also approaches negative infinity, right? This is going to keep going this way as we go left. And as x approaches infinity, y approaches positive infinity. Okay, so again, important things to know. On rational functions, when you graph it, make sure asymptotes are shown with dotted lines, holes are shown with an open circle. Whenever you have a vertical asymptote, you will have something on both sides of the vertical asymptote, so make sure you are looking for branches on both sides. Sometimes scales will be off and only one branch will show up on the graph, especially if you're using a graphing utility, depending on your window. Okay, so you're always on a vertical asymptote, you are looking for a branch on either side.